So let us now look at the discharging method. Okay. So we start with a very small example, a trivial example. In fact, to prove this, you don't really need any discharging method or anything. We can directly prove it from some of the simple results that we have studied. But we want to use it to just start, an idea of discharging. So we want to prove the following. Every planar graph has a vertex of degree less than or equal to 5. And we want to prove it using the discharging method. So how do you do this? So we start with the graph, which is a planar graph, and consider some embedding of this graph on the plane. Okay? Because it is planar, I have a plane embedding. So let us look at this plane embedding of the graph. Now what we do is that once we have this embedding, we assign charges to the vertices and faces as follows. Okay? So given a graph, what we will do is that we look at every vertex and then say that this vertex gets a charge equal to its degree minus 6. So this vertex is degree 3, so therefore it will get minus 3 charge. Okay? This was vertex degree 2, therefore it will get 2 minus 6, which is minus 4. Here I will get 4 minus 6, which is minus 2, 1 minus 6 minus 5, 5, and minus 3, right? So all the vertices get a charge, its degree minus 6. I mean, if you have degree 10, you will get charge 4, right? If degree 20, then that vertex will get charge 14. Then every face of the graph is also given a charge. It's twice the length of the face minus 6. Okay. So length of the face is the number of edges in the boundary of the face, right? So what are the edges that define the boundary of the face? So that number of edges is the length of the face. Okay. So the number of faces in the boundary, a number of edges in the boundary is the length. So therefore, if you look at this face, it has 3 edges in the boundary. So therefore, its length is 3. So its charge will be 6 minus 6, which is 0. Again, 2 into 3 minus 6 is 0. But if you look at the outer face, it has 1, 2, 3, 4, 5, and 6. So it has 2 into 6, 12 minus 6, which is plus 6 for the face, outer face, right? So this way you assign charges to the graph, right? Now I want to look at the total charge in the graph. So what is the total charge? It is the total of all the vertex charge plus all the face charge. So it's summation over all the vertices, charge of V, plus summation over all the faces, charge of F. Summation over all the vertices, charge of V, plus summation over all the faces, charge of F. Now what is this? This is summation, right? Overall V, charge of V is degree of V minus 6, and charge of F is twice the length of the face minus 6. But now, what is summation over all the vertices degree of V, right? This was one of the earlier results that we studied in graph theory. This is the sum of the degrees is twice the number of edges. So therefore, the first term will give you twice the number of edges, right? 2e. Now, we are subtracting 6 minus 6 as a constant for every vertex. So there are exactly cardinality V many vertices. So therefore, minus 6b. Now, similarly, a face, right? An edge is incident to at most 2 faces. So therefore, if you sum over all the faces, you will get at most twice the number of edges, right? 2e. But now we have two times cardinality of F, right? Length of F. So therefore, it is 4 times, right? At most 4e. and then minus 6, which is over all the faces, so it's minus 6. So I will get 6 into, right, E minus V minus F. But this by Euler identity for a planar graph, the number of edges minus number of faces minus number of vertices is minus 2, right? So therefore it is 6 into minus 2, which is minus 12. So the total charge is at most minus 12, right? So what can we conclude from this, right? So no matter what planar graph that we started with, we see that the total charge is going to be less than or equal to minus 12. But if the total charge is negative, then some guy, right, some elements in the summation must contribute negative value, right? What are the negative values that is contributed by this element? If you look at any phase, right, every phase boundary is at least 3 edges, right? So the length of any phase is at least 3. So therefore, if you look at 2f minus 6, 2f minus 6 is always greater than or equal to 0 because the length of any phase is at least 3. So this is greater than or equal to 6. So therefore, 2f is greater than or equal to 6 and 2f minus 6 is non-negative. On the other hand, for a vertex, its charge is degree minus 6. Now the total charge is negative. If you sum non-negative numbers, you are not going to get total to be negative. So therefore, some charge should come from a vertex which is negative, right? Because phases are all giving non-negative values. Vertices must give negative values. So it says that some vertex should give negative value, and a vertex which gives negative value cannot have degree greater than 5, because if the degree is 6 or more, its charge is also non-negative. So therefore, there must be some vertex whose degree is less than or equal to 5. Now this tells, apart from just showing that there is a vertex of degree less than or equal to 5, it tells that if you assume that the minimum degree of a planar graph is 5, then you should have at least 12 vertices of degree equal to 5. Right? This is an additional information which you don't get from the other, right? Because if you look at a planar graph where the minimum degree is 5, then since the total is minus 12, each vertex can only give minus 1 to the sum. So therefore, any planar graph with minimum degree 5 should have 12 or more vertices of degree equal to 5. So this also tells that if you make graphs with minimum degree 5 on, let's say, on 8 vertices or 6 vertices or 10 vertices, right? These are all not going to be planar, right? They are going to be non-planar. Okay. Now let us look at a more interesting example to see what exactly is the discharging method about. So let phi be a class of plane graphs, right? It's a planar graph with a plane embedding, right? Phi be a class of plane graphs with minimum degree at least 3. Okay? So every vertex has degree greater than 3. And we assume that these graphs does not have cut vertices, just to make our argument simple. So we'll assume that we are looking at plane graphs where the minimum degree is 3 and does not have any cut vertex. Okay, this is the class phi of graphs. Now, we have a property P. Okay, so the property that I define is P of G is defined as follows: that there is some vertex, and this vertex, right, it's a plane graph. So this vertex is incident to a face F, right? Because once you have an embedding, every vertex is incident to several faces, right? So a vertex is incident to a face F, such that the degree of the vertex is D and the length of the face, right, the number of edges in the boundary of the face is L, and D plus L is less than or equal to H. Okay, so the property P says that, right, you can find some vertex which is incident to a face for a plane graph, a vertex incident to a face, such that the length of the face plus the degree of the vertex is at most 8. You can always find if the minimum degree is at least 3 and there is no cut vertex. This is the plane. So the graphs in pi satisfy property P. So if you are looking at plane graphs with minimum degree 3 and no cut vertex, then it will have always a vertex and adjacent face whose sum is at most 8. So we want to prove this. So we are going to use discharging method to prove this. So let us start with a simple graph example, just to as a working example. So we start with this graph. Okay. So it has all these vertices, right, and edges which are defined. And then now I am going to give some charges as before, right? We are going to give charges. So for discharging, we need charges. So what is our charge, right? So the charge is the following, right? So the charge rule is the following, that every vertex gets a charge its degree minus 4. Okay? Every vertex gets a charge its degree minus 4. And every face gets a charge the length of the face minus 4. Now, once this charging is applied, what happens to the graph? Well, you can see what are the charges after the charging phase, right? So after the charging phase, you will see that these vertices have, for example, this one has initially degree 4. So the charge is 4 minus 4, which is 0. It had 3, so therefore 3 minus 4, which is minus 1. Then similarly, it had 5, degree 5, therefore it has charge 1. So 0, 1, 0, minus 1, etc. And for the faces, for example, this face had 1, 2, 3, 4, 5, and 6, right, edges in the boundary. So therefore 6 minus 4, which is 2. Similarly, other faces will get its charge 0 or minus 1 or 2, etc. Right? So all the vertices and faces gets its charges. Now, the idea of the discharging method is to somehow show some structural property of the graph, right? So in this particular example, we want to show some vertex which is incident to some face, right? So that the the degree of the vertex plus the length of the face is at most 8. Okay? Now, since we are looking at vertex face incidence, let us define a vertex face incidence. Okay? So I define the vertex face incidence of a graph as a corner. So what do I mean is that when a vertex like this is incident to a face like this is a corner for me, right? So vertex face incidence, because it looks like a corner. So I'm just defining a term which is not in standard graph theory, just for the purpose of this problem. So I define a vertex face incidence as a corner. Now, before doing anything with the corner, I observe that what is the total charge after the charging phase, right? So if I look at the total charge, it is summation over all the vertices dv minus 4 plus summation over all the faces length of f minus 4, right? Which by earlier observation, right, similar calculation, it is 2e minus 4v plus 2e minus 4f, which is 4 into e minus v minus f, which is 4 into minus 2, which is minus 8. So if we started with this, you will always get minus 8 as the chart for connected graphs, right? With the property that we are looking at, we will. So again, we will assume that the graph is connected, because for each component we can see whether the property holds, and we can do some some small modification to the proof to do it for all graphs. So we'll assume the graph to be connected for the time being. Okay, so for connected graph, we can use the Euler identity to show that the total charge is minus 8. Now, so we define the incidence of a vertex and a face as a corner, and then here are some examples, right? So you have this vertex here, and you will see that it defines its degree is 3. It has exactly 3 coordinates. For example, this corner, and this corner. Similarly, this has 2 coordinates. Each vertex has several coordinates we can define, right? Now, once you have this, let us look at what we can do further with this idea. So we are going to define a discharging rule. So this is the reason it is called discharging method, because after the charging phase, we do a discharging phase. Okay. So in the earlier example, very simple example, we didn't do it, but in general, we do a discharging. So what is the discharging rule? Discharging is basically moving around the charges without losing anything, right? We just move around the charges. So transfer the charges from one place to other, etc. So in this example, our discharging rule is the rules are the following, right? So the first rule is that every vertex distributes its charges equally to all of its coordinates. Okay? So it gives away all its charges to all its coordinates. Okay? Whatever I have, I am going to distribute it to all of you, right? Then every face, right, distributes its charges equally to all its coordinates. So again, a corner is a vertex face incidence. So when I have a corner, it has a vertex as well as a face, right? So the face has several coordinates. Vertex also has several coordinates. So each face gives its charges equally distributed to each of its coordinates. So this is the discharging rule. So what is the meaning of this statement, right? This says the following, that this says that okay, let us observe something before we go into that. Suppose a vertex is not a cut vertex. Okay, so if it is not a cut vertex, then I want to observe that this vertex is incident to exactly its degree many distinct faces. So what I am saying is that if this vertex x is not a cut vertex, then this faces f1, f2, f3 to f5, right? All these faces are all distinct. If they if one of these two faces is the same as the other face, then the vertex will be a cut vertex. That is the observation. Okay? You can think about why. Okay. On the other hand, if x is a cut vertex, you will see that you may not have this property. That, for example, the degree is here 4, but there is only 1, 2, and 3 faces, right? Because this side and this side are the same face only, right? Part of the same face. So therefore, if a vertex is not cut vertex, right, then we will see that it has exactly its degree many distinct faces incidentally. So it has exactly that many coordinates also, right? Again, it is very easy to see that if you have a cycle, right, or a face, then it has its vertices, and the number of the length of the face and the number of coordinates are the same. So that is the fact too. If G has no cut vertices, every face is incident to length of the face many vertices, right? Because it's basically a cycle. Boundary is a cycle. Cycle has exactly number of edges and number of vertices to be the same. Now, from these two observations, we can see what the discharging rule does to the uh, charges, right? So the discharging rule says for a corner v dot f, its new charge, right? The charge of the corner will be like if phi dash is the charge for the corners, then for any corner v dot f, right? Phi dash of f v dot f will be from the vertex v, the corner will get the degree of the vertex minus 4, the initial charge, divided by degree of v, because the vertex v distributes its charge equally to all its faces, right? So it has exactly dv many faces. So therefore, it distributes its charge to the dv minus 4 charge to each of the degree of v many corners, right? So therefore, it will be divided by d of c. So that is the charge given by the vertex to its corner, and the face, its charge is a length of f minus 4, and because the face has exactly length of f many vertices, that many corners are also there. So therefore, that face also gives length of f minus 4 by length of f charge to the face. So this is the only charge the face is the corner is going to get, and therefore the charge of the corner is going to be this value. So for every corner, you see what is the charge that it has. Of course, what happened to the vertices charge? It has all disappeared, right? It has given away its charge, whatever positive or negative, equally to its coordinates. Similarly, all the faces have given away the charges. So the faces and vertices now have zero charge. So here is the rule in action, right? The vertex with the degree 1, right? Degree 5, degree 5 has charge 1. It gives charge 1 over 5 to each of the 5 coordinates. So in particular to this guy, right? It gives a charge plus 1 by 5. Similarly, the corresponding face, right? F, it is also giving a charge. Its charge is minus 1. It has exactly three neighbors, right? 3 corners. So minus 1 by 3, right? Minus 1 by 3. So that charge goes to this corner. So this corner gets plus 1 by 5 and minus 1 by 3. So the sum of these two will be its charge, right? Similarly, for each corner, you will get. So once the discharging completes, you will get something like this, right? The total charges in each of the vertices are going to be all zeros, right? And charges in each of the vertices will be zeros. Charges in each of the faces will be zeros. And then the corners will have some charges. But now our observation is that the total charge of, the charges have all moved to the corners. So the total charge will be in the corners will be the same as in the total charge we had earlier, because we just moved around the charges, right? We just shifted the charges from the vertices to the corners, but we did not change it, right? We did not lose it. So the total must be the same. So the sum over all the vertices and faces, the charges of the corners is minus 8, right? Because minus 8 was the earlier sum of charges. Since the total remains the same, the total is again minus 8. But if the total is negative, then as we observed earlier, at least some of the charges must be negative, because if everything is non-negative, the sum is going to be non-negative. So it says that there must be some corner with negative charge, right? So we can find such a corner, right? We said that since there is there is a corner with negative charge, you can pick one of them. So we see that, okay, there is some corner with a charge less than 0, which we find, right? So pick one of them. Now, if you take any such corner whose charge is negative, let us see what happens to it, right? So what is the charge? The formula is degree of the vertex minus 4 by d plus length of the face minus 4 by L. Now this value is the charge of the face, and this particular face has d minus 4 by d plus L minus 4 by L as a charge, which is negative, right? Less than 0. But we know that the degree of any vertex is at least 3, because by assumption the class has minimum degree 3. And the length of any face is of course at least 3, because faces are all cycles, and this the boundary will have at least 3 edges in the boundary. So therefore D and L are at least 3, right? So we have this inequality. Now we can just resolve this inequality by some routine calculation. Okay? So which is what we do here. So we have d minus 4 by d plus L minus 4 by L is less than 0. Just cross multiplying, we will get 2LD minus 4L minus 4D is less than 0. And this says that D is less than 2L by L minus 2. Now, 2L by L minus 2, when L is at least 3, you will see that it is less than or equal to 6, and similarly L is less than 2D by D minus 2, again from the same equation, which is also less than or equal to 6. So for L greater than or equal to 3 and D greater than or equal to 3, we have these two inequalities. Now let us just add L to the first inequality. Let's say D plus L. So D plus L is now less than this plus L, which is L square by L minus 2, right? Because 2L by L minus 2 plus L, L square minus 2L, 2L will cancel, L square by L minus 2. But now D plus L is less than L square by L minus 2 from this inequality. But we know that since L is between, right, L is at most 6 and L is at least 3, and if you substitute that for L square by L minus 2, you will see that D plus L is going to be less than or equal to 8. And because L square by L minus 2 is going to be less than or equal to 8. And that is it. So we have proved that for all the corners whose charge is negative, this identity is true. And since there is at least one corner whose charge is negative, we get that you can find such a pair of vertex and face incidence. So what we did in this was the following, right? We started by giving charges to the graph, right? Vertices and faces. Then we use Euler identity to show that the total charge is a negative number, right? And basically, we can show that it is less than 0. That is sufficient. And then what we do is that we use some property of the class that we are looking at. For example, degree is at least 3, right? Planar graph, etc. Right? Some property to move around the charges and then use it in a nice way. That depending on what we want to show, we have to do it. But we basically define some rules of discharging, that moving around the charges. And after moving around the charges, we again the sum, right? We did the sum again, right? But what we know is that if you move around the charges, the total charge cannot be different. Right? So after moving around, what we want to say is that if certain structural properties are not there, for example, like the one that we saw, we establish that the sum will be always different. So we say that because the sum cannot be different, the property must be there. So that is the overall idea of the proofs that we were looking at. So this is how one can use discharging method to prove results on graphs, and especially planar graphs, it is very powerful. So what we are going to do is we will look at one more example, which is a more involved example to see a better picture of the discharging.